Good morning to everyone. In the previous presentation, we discussed about the photon picture of light, as well as we discussed about the photoelectric effect. In this particular presentation, we are going to discuss about the experimental setup of the photoelectric effect, and the experimental setup is not that complicated. It is a very simple setup. As we can see, this experimental setup basically consists of two metal plates which are sealed inside a vacuum chamber. The two metal plates are mainly the cathode and the anode. As we all know that cathode is mainly the emitter in this particular experiment. Now you see, when we have the electromagnetic radiation as it is depicted in the yellow color, when the electromagnetic radiation falls onto this cathode plate, the electrons are emitted out of this cathode plate because cathode mainly acts as an emitter. And when the electrons are emitted by the cathode, they basically reach the anode, and when it passes through the emitter and all that stuff, we have the batteries. We may also put a rheostat. We may put an emitter here, and when the electrons pass through this particular electrical circuit, we say that when the electrical current is detected in the emitter, we say that the electrons for sure have been emitted by the cathode, and therefore the photoelectric effect has taken place. So this is basically the fundamental setup, because this is how you gather the evidence of the photoelectric effect, that when the electrical current is established inside the circuit, you say that yes, for definitely the photoelectrons have been emitted out of the cathode plate, and therefore the photoelectric effect has happened. Now this anode potential can be positive as well as negative with respect to this cathode. Yeah, because the potential at anode is arbitrary. Okay, the potential at anode is arbitrary. We can have a potential which is positive with respect to the cathode, or we can have a potential which is negative with respect to the cathode. Now what happens when the anode potential is positive with respect to the cathode? What happens? So we are taking the first case when the anode potential is positive with respect to the cathode. Is positive with respect to the cathode. Now before that, it's a very basic and understood thing here, that when the electrons come out of the cathode, we do not want any collisions. And now you must have understood that why we are keeping why are we keeping this particular setup inside the vacuum chamber, because we do not want these electrons to collide with the air molecules. Okay, we want every electron which is coming out of the cathode to reach the anode and therefore contribute in the electrical current. We don't want electrons to get scattered here and there because of the air molecules. Now what happens is that after some period of time, when the electrons are crossing this particular path and they are reaching anode, this particular space between the cathode and anode becomes charged, negatively charged. Of course, because it's a complete vacuum, and there is a transfer of electrons from the cathode to anode. So obviously this particular region between the cathode and anode becomes negatively charged. Now what happens further? See, if this phase becomes negatively charged, any further emission of electrons from the cathode side would be repelled by these electrons. This is for sure, right? Because the space is negatively charged, and when more electrons would be emitted out of the cathode towards the anode, the electrons will be repelled by the electrons which are present inside. So therefore, but still few of the electrons which have maybe high velocities or which are having a high kinetic energy would be able to reach this anode. Now what happens if we provide anode with a positive potential with respect to the cathode? Now if this becomes positive, you know that the electrons inside would be attracted towards this anode, and when the electrons would be attracted towards this anode, the photocurrent would increase. Yeah, it's a very basic phenomena that if you put a positive, if you give a positive potential, because we have battery here, so we can control the potential of the anode with respect to this battery, or we may also have rheostat and all that stuff. So we may make this potential of the anode positive with respect to the cathode, and therefore the electrons would get attracted towards the anode, and therefore the photocurrent would increase. So we say that anode potential is negative with respect to the cathode. So as a consequence of it, the photocurrent would increase. Photocurrent would increase. We can also have a graphical graphical representation of the same. If I if I use a shape, yep, use a shape. If I use a simple graph, the graphical representation. I use a graphical representation, and if I plot, let's say this is current I, and this is the potential of the anode. No, the graph is going to look something like this. And at one point of time, this will saturate here. So we may name this region A, B, and C. As it is understood, as we go on to increase the positive potential on the anode, the saturation current will increase. But you see this region BC, this is where the current becomes constant. And why does this happen? Now this happens because as you go on to increase the positive potential on the anode, there would be a time when this effect of space charge, as I just discussed, here, that there is a space charge inside which is negatively charged. There would be a time when this anode potential would be tremendously high, and therefore every electron that comes out of the cathode reaches the anode, and there is no further repulsion of the electrons that are present here uh, 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 to the incoming electrons. There is no further repulsion, so every electron that comes out of the cathode reaches the anode. And in this particular presentation, not presentation, in this particular situation, the effect of the space charge becomes negligible, and every electron that comes out of cathode reaches the anode, and therefore the current becomes constant. And if you want to increase the current, then there is only one way you could increase the intensity of the light. Otherwise, if you change the potential difference, make this anode potential more positive, the current would not increase, the current would be constant. So therefore we have discussed first case in which the anode potential is positive with respect to the cathode. I'll just repeat it. The space charge is negatively charged. If you make this anode potential positive, the electrons would get attracted towards this anode, and therefore the photocurrent would increase. But there would be a time when this anode potential would be very positive, so much positive that the effect of the space charge becomes negligible. And when this happens, every electron that comes out of the cathode reaches the anode, and therefore the current becomes constant. If you have to increase the current further, if you have to increase the saturation current further, there is only one way to do that, that is to increase the intensity of light. So basically, when more number of electrons collide, when more number of photons collide with the electrons here, more interaction between the photons and the electrons take place, then maybe more electrons are emitted out of this cathode, and therefore the photocurrent would increase. So we also get a very interesting and important result out of here, that photocurrent depends on the intensity of light. As we just discussed. Now there is another way. You could also make this anode potential negative with respect to the cathode. You make the anode potential negative with respect to the cathode. And then what happens? Now, if you make this anode potential negative with respect to cathode, then what happens? Now, as I just discussed, that this space is negatively charged, and when you make this anode negative with respect to the cathode, then then when the electrons come out of this cathode, they will be repelled by this anode, and some of the electrons that are present here may also get back to the cathode, and therefore overall the saturation current would decrease, as it is very obvious. This is negative, the anode is made the potential of anode is made negative with respect to the cathode. Electrons are coming out of the cathode, and when this is negative, the anode potential is negative, there is strong repulsion by this anode to the incoming electrons, and therefore few of the electrons get back into this cathode, and then the overall current, the photocurrent, decrease in this particular circuit. Now, there is one interesting case in this particular aspect. Like, we discussed the concept of saturation current when the anode potential was positive. There is a concept of stopping potential when the anode potential is negative. Now, what is stopping potential? Stopping potential is that particular potential when the photocurrent becomes absolutely zero. So we may say that even the fastest electron, or I may say that the electron which has the maximum kinetic energy, it also fails to enter anode. Yeah, so we may say stopping potential. There is a very interesting concept of stopping potential, and we will just calculate what is the value of the stopping potential. But to understand this, we must find a criteria, and the criteria is that even the electron with fastest speed or maximum kinetic energy fails to reach anode, because it is very obvious that if an electron with maximum kinetic energy fails to reach the anode, then obviously other electrons which are having less kinetic energy would never reach the anode. Now, to understand this, we must see, if you look at this diagram, you see when this anode potential is negative, obviously what happens to the electron with the maximum kinetic energy? Now, when this electron comes out of this cathode and it enters into this region, its kinetic energy decreases, because there is an increase in the potential energy, and obviously increase in the potential energy leads to the decrease in the kinetic energy. By how much amount does the potential energy increases when the electrons are emitted out of this cathode, or the electron which is having maximum kinetic energy is emitted out of this cathode? The increase in the potential energy is EV naught. We all know it, it's basic. Yeah, so the increase in the potential energy is EV naught, but this particular increase in the potential energy leads to the decrease in the kinetic energy. So when this electron reaches to anode, what is the kinetic energy? What is the total energy that remains? What is the total energy that remains? The energy that remains, remaining energy, just let me adjust. Remaining energy of the electron is its maximum kinetic energy, which was the energy when it came out of the cathode, because obviously we are talking about the electron which is having the maximum kinetic energy, and minus the decrease in the potential energy, the increase in the potential energy, which eventually leads to the decrease in the kinetic energy. So this would be the maximum, this would be the energy of the electron when it reaches the anode. Now we are looking for the situation that even the electron which is having maximum kinetic energy fails. So obviously what would have happened is that all of its kinetic energy would have been consumed in the potential energy. So basically all of its kinetic energy gets consumed into the potential energy, and therefore it does not have any further kinetic energy to reach the anode. And what would be the condition for that? Obviously the maximum kinetic energy becomes exactly equal to the potential energy, and therefore it does not have any further kinetic energy to reach the anode. So this is the situation in which the electron which is having maximum kinetic energy fails to reach the anode. Now we know what is the expression for this maximum kinetic energy. We have just derived in our previous lecture. The expression for maximum kinetic energy is hc by lambda minus psi. So the expression for maximum kinetic energy is hc by lambda minus psi. This is equal to ev naught, and from this particular value we can, and by the way, what is this v naught? This v naught is exactly equal to the stopping potential. Yeah, this maximum kinetic energy, this must be equal to ev naught. This ev naught is the potential energy, where v naught is the stopping potential. If we compute the value of v naught from here, we get hc over E times 1 by lambda minus psi by E. This is exactly the expression for stopping potential which we need. Now, few of the interesting observations from this expression. First of all, this V naught, it depends on the wavelength. Yeah, very evident from the above expression that it depends on the wavelength lambda. Second, it depends on the work function. Depends on the work function. Third most important thing, that stopping potential does not depend on the intensity of light. Does not depend on the intensity of light. This means that, let's say you have 1 watt source of of light. Let's say you shine 1 watt of light onto some particular metal surface, and for example, let's say minus 2 point or say let's minus 2 volts of stopping potential is required to stop the fastest photoelectron. Even if you use a source of 100 watts, same 2 volts of stopping potential would be able to stop the maximum the electron which is having the maximum kinetic energy. So this stopping potential does not depend on the intensity of light. It's very, very important. Stopping potential does depend on the wavelength. Stopping potential does depend on the work function. It is very evident from the expression here. But this stopping potential does not depend on the intensity of light. This is very, very important. And we know that this stopping potential from this particular expression star, we know that this stopping potential is related to the kinetic energy. Yeah, because this kinetic energy maximum is equal to EV naught. So therefore this stopping potential is related to the kinetic energy, and therefore we can say that even kinetic energy does not depend on the intensity of light. Very, very, very important. And it is often asked in the exams that is kinetic energy dependent on the intensity of light? The answer is strict no. As you can see, the stopping potential does not depend on the intensity of light. The stopping potential is related to the maximum kinetic energy, and therefore we can conclusively say that even the kinetic energy does not depend on the intensity of light. This is the point where this particle behavior of light this is the point where where the wave nature of light cannot explain this. According to the wave nature of light, the maximum kinetic energy should depend on the intensity of light. Why? Because you know it does not matter, because if you say, if you have a source which has very high intensity, then the energy is not discrete. The energy is continuous according to the classical behavior. If the energy is continuous, then the electrons that are present inside the metal will get energy slowly and steadily, and at some point of time the electrons may come out of the metal surface and do this all and the photoelectric effect would have been possible. But this is not the case. This is not the case. Even if you have a very very high if you have a very very high intensity if you have a very very high intensity of the source, it does not matter uh, uh, if the energy is not greater than the work function. It does not matter how much high is the intensity, the electrons will not come out of the metal surface, and the photoelectric effect will not take place. So a very very important fact is that even the even the kinetic energy is independent of the intensity of light, and therefore I should write it. Kinetic energy maximum does not depend on the intensity of light. On the intensity of light, this particular observation cannot be explained using classical physics or using wave theory. Yeah. So if you look at this expression, we can also plot this expression. If you look at this expression carefully, this expression looks similar to y is equal to mx plus c. Yeah, y is equal to mx plus c. If you plot this v naught with respect to 1 by lambda, this would be the slope and this would be the intercept. So if you plot this particular expression, yeah, I'll use this, or maybe I'll use this. Yeah. Yeah, I'll use this. Now, if this is V0 and I'm plotting this graph with respect to 1 by lambda, okay, so I can use shape. This would be the graph. Yeah, this would be the graph, and what the slope of the expression, the slope of this line, if we compare the above equation with y is equal to mx plus c, this m is the slope, then the slope comes out to be hc over e. This would be the slope, and the intercept would be psi over e. So this would be the intercept. This would be psi over e. And if I give you the real datas, and if you find a plot of a metal, this v0 over 1 by lambda, you could actually calculate the value of the Planck's constant, because this c and e would be they are fundamental constants, if you calculate the slope, if you have the real time data of any metal, you can actually calculate the value of this stopping potential, which is done in which we usually do in our schools or maybe in our colleges. Yeah, so this is all about the photoelectric effect. Just one more thing that I would like to make clear as to why the wave theory is not wave theory does not explain this particular another interesting observation. You know, uh, wave theory says, let's say for example, let us take a weak source. Okay, let us take a weak source of light. Wave theory says that first of all, it does not explain as to why there should be a cutoff wavelength, as we just discussed in the previous presentation, that there has to be a maximum wavelength, which we called as the cutoff wavelength, and if the wavelength of the light that we are using is greater than that cutoff wavelength, then no matter what is the intensity of the light, the photoelectric effect will not happen. This particular observation also cannot be explained using the wave theory of light. Wave theory of light says that wavelength of the light does not matter. Okay, even if you have a strong source, source means that when I'm talking about this strong source, I mean a source which has very high intensity. So wave theory of light says that a source which has high intensity, definitely if you use that particular set of experiment, for sure the photoelectric effect will take place. Now in this particular example, we are talking about a weak source of light. Wave theory, how will the wave theory of light explain the photoelectric effect? When this is, wave theory will say that okay, it's a weak source of light. Weak source of light means the number of photons that are falling onto the metal that are falling onto the metal are very less, which means that the intensity is very less. Therefore, after the instantaneous emission of electrons will not take place. The intensity of the photons are very less. The energy will continuously spread to every electron, and after some particular time, the electrons will come out of the metal. But in experiment or in reality, this does not take place. Okay, even if you have a source which is very very less intense, okay, or the intensity is very very less, if the energy of the incident radiation is greater than the work function, then for sure the photoelectric effect takes place. This is certainly definite. So the intensity of light does not matter. What matters is that the lambda should be lesser than the cutoff wavelength, or you can say that the energy of the incident radiation should be greater than the work function. Intensity of the light does not matter. So this is so this is an important observation. If I could write down what I just explained, let us take a weak source of light. The wave theory of light could not explain instantaneous emission of electrons from the metal, because according to wave theory, it's a weak source. So it's a weak source. If it's a weak source, intensity is very less. So it will take some time for the electrons to gather that particular energy and come out of the metal. Whereas the photon picture says that it is not at all necessary if it's a weak source or it's a strong source. If it satisfies the criteria that the wavelength of the incident light should be lesser than the cutoff wavelength, electrons will come out instantaneously. And instantaneously, I mean, 10 raised to the power minus 9 seconds. So it is that instantaneous. You shine a beam, instantaneously the electrons come out. This particular thing cannot be explained using the wave theory. Therefore, we can say to explain the photoelectric effect, the wave theory has failed. And this is what I wanted. This is what I wanted to explain. Thank you very much.